some feedback? Yeah, okay. So last time we started talking about the idea of using CLP and this calculus that we have developed for convergence and distribution conversion probability to state a result without the fluctuations of our estimator around the mean. So it's always good to remember that the two basic convergence results in probability are we can reformulate as statements or statistical statements. The first one is saying that the sample mean is consistent for the population mean. That's the weak law of large numbers. And the second statement tells you something about the fluctuations or deviations of the sample mean around this limit. So this is roughly saying that if you take the root and times this deviation, the deviation stabilize in the sense that the distribution converges to a normal random variable. And if you recall last time we talked about, so we had this, just let me remind you, we had this proposition that connected these ideas, and we're going to heavily use that. Something to note is like the continuous mapping theorem. If you apply a continuous function to a sequence of random variables that's converging in the distribution or in probability, then the result is still going to converge in the same sense to f applied to the limit. And there's this Slutsky's result, which is really important for us. So if you have two sequences that are converging, one is converging to a constant, the other to some random variable potentially, then you can say that the joint distribution converges to the joint distribution of let's say x and c, and then you can apply the continuous mapping theorem to get all sorts of interesting statements like x1 plus y, xn plus yn converges to the sum of the two sequences converges to the sum of the limits. The product converges to the product of the limits. We can divide. And this works for matrices like vectors, things like this as well. So this could be a matrix, random matrix. This could be another random matrix. And this is the inverse of this random matrix times the other one, as long as the matrix is converged. So everything works in a general metric space, more or less. So we talked about an example, which I'm not going to go through. And then we arrived at this uniform tightness idea, which is equivalent to big O notation. So this characterizes, it's the right notion, probabilistic notion of boundedness. So you have a sequence, the sequence, let's say random vectors are uniformly tight or bounded in probability if this condition holds. For every epsilon, there exists some m such that the probability that the norm of the sequence is bigger than m for all n is bounded by epsilon. So uniformity is here. So you can show that, for example, every there's like a Radon random variable, but like every random variable, like for like random variables in R, they're always tight. So if there was just one single random variable, if I had a single random variable, a random vector, I can always find m. Given any epsilon, I can always find m such that this is less than epsilon. This is saying that the mass, this is similar to the idea that you had in your homework that if you have a density, the limit, as you go to infinity, the density has to go to 0. So you can't have more and more mass piled up at infinity. So this is saying, if I look at the norm, basically, so for a single random vector, this is like saying for every epsilon there is an m, or equivalently for every epsilon there is some m such that the norm of x is less than 1 minus epsilon sorry, 1 minus m for like with probability at least and m with probability at least 1 minus epsilon. So given any like level, like 0.99, I can find an m such that it contains all like 99% of the mass. So if I go that far, like put a ball of radius m, I can contain 99% of the mass of the distribution. That's really intuitive. And this holds in general, like very general settings. We can define more exotic random objects in metric spaces under some mild conditions. This would hold. This is saying for a sequence, basically, you can take that m to be the same for all of these random variables at some point. So I picked a ball, and the ball contains the bulk of the mass of everyone after a certain point. I don't have to worry about this m depending on n. So that's the uniform tightness idea. So two important properties is that if something goes to 0, the sequence goes to 0 in probability, and I have a uniformly tight sequence, and the product is going to 0 in probability. And a more important one, both are important, but this is saying if a sequence converges in distribution to something, then xn is uniformly tight. So for example, and then we use this big O notation. So we write xn is big OP of 1 if the sequence is uniformly tight. So remember, xn is a little OP of 1 if xn converges in probability to 0. Right? So big O and little o are familiar from real analysis. This just upgrades it to the probability sort of domain, or it's like the right notation, or right notions of like they're basically a stochastic ordering sort of. They tell you, and there was a question last time, I guess. What was your name? Sorry, Sibel. Okay, so Sibel asked, what is this 1 here? And basically what it is saying is that xn over 1 converges to, let's say if I have xn is little OP of 1, what it is saying is that xn divided by 1 is converging to 0. So I can have like xn is little o p of yn. This is saying that xn over yn goes to 0 in probability. So 1 is the same idea, similar idea to the little O notation. It's sort of an ordering. So this is saying this goes to 0 faster than this in probability. Okay, so the ratio still converges to 0, which is saying that xn goes to 0 faster. And the same goes for the big O. So this is saying xn divided by 1 is tight. So I can put something else here. This would mean that xn divided by yn is tight, or uniformly tight. The consequence of this fact, for example, the consequence of B is that if I have root n, let's say xn minus, let's say some parameter theta n converges in distribution to something, because it's converging in distribution, then it means that root n xn minus theta is big OP of 1. That's part B. And so this is telling me that xn minus theta is OP of 1 over root n. I can divide. That's the idea here. So you can see that this means that this divided by 1 over root n, which is basically this, is OP of 1. So you can write these notations. And this makes very intuitive sense. It just says that it just says that what would you expect? I mean, it says what you would expect. So this is saying xn is theta plus big OP of 1 over root n plus a fluctuation which is bounded, something bounded divided by root n. So it's going like 1 over root n to 0. And you see this notation a lot. And once you get comfortable with it, it just makes a lot of sense. So for example, CLT tells you that because we know that this is converging to normal 0, let's say sigma squared, CLT, then it says that xn is mu plus big O P of 1 over root n. Instead of writing things like informally, you can formally write something like that. And so this is the rate of convergence. So xn converging to mu at the rate which is 1 over root n. So you can think of CLT as CLT provides the rate of convergence or rate of consistency. So weak law of large numbers tells you things are consistent in the limit you converge to the truth. CLT tells you how fast you converge. And this is not that fast. So that's the traditional, this is called root n consistency. It's the typical root n consistency. Basically, it's a fact of statistic that the variance of the sample mean converges to 0, like 1 over n. So the standard deviation is 1 over root n, is what you see here. It's relatively slow. So if you have 100 samples, this is going to go down by a factor of 10. If you want it to go down by another factor of 10, you need like 10,000, right? So you have to, because it's square root, you have to have a square of whatever factor you want to go down in terms of the sample size. So this is usually the parametric rate. We'll see, for example, something like this holds for MLE in general. In more exotic situations like non-parametric statistics, high-dimensional statistics, you could get rates that are even slower than this. And so one of the like ongoing, or one of the open problems in statistics, always finding the rate of convergence for a certain class of problems. Depending on the rate, you can think about the hardness of the problem. So every problem that has the same scale of convergence as this is basically in the same ballpark in terms of hardness of like estimating a mean, or most of the parametric problems are like this. But something that has like a convergence rate of 1 over, let's say, n to the q, like 1/3, that's a harder problem. If you can if you can't improve the bound, you need much more samples to get the same accuracy. That's sort of the difficulty. So any questions about this? So let's now use these online people questions. So let's now use these ideas. Actually, no, we still need one more idea. So that's the thing that I had added. It's a little bit technical, but the idea is very simple. So we need one more concept. So we have uniform tightness, and we also need stochastic equicontinuity. So I'm writing SEC. If you're in finance, this has a different meaning, but stochastic equicontinuity, it's not Securities and Exchange Commission. So stochastic equicontinuity, a sequence of functions is stochastically equicontinuous at theta naught if this complicated looking statement holds. So what this is trying to capture is some sort of idea of uniform convergence along the sequence of functions. So we know uniform convergence for a single function. Suppose now I have a sequence of functions or a class of functions. I want to say that, let's say each one is continuous, but the continuity is sort of uniform across the function space. So if I go through this, maybe this is easier. This is the classical equicontinuity for real analysis. So if I have a class of functions, I have a collection of functions. The script f is a collection of functions. We say that this collection is equicontinuous at theta naught if for every epsilon there exists delta, such that whenever I'm delta close to theta naught, the value of the function is close to the value at theta naught for all the functions in the class. So this for all the functions is the uniform part, or continuous part. So the same delta works for everyone in the class, similar to the uniform continuity where the same delta basically works everywhere in the domain. So So that's the deterministic. This is easy to understand. So without, if you discard this, this is just the definition of continuity. This is just saying that this part holds for all f. I can reformulate this as saying this part is the same. If I take the supremum over all the delta that are in a ball of radius theta, so this is just saying that theta is such that the d of theta and theta naught, this is the distance of theta and theta naught, is less than or equal to delta. So this exact statement is this. So supremum over all theta that are in this ball and also over all f, this deviation is bounded by epsilon. For all theta that are close and all f in the class, the value of the function is close to theta naught, epsilon close. So that's equicontinuity. If you think about the fact that these are deterministic, you can just, let's say, put a probability here around this. The probability of the complement of this would be 0. So this is still the same as this. The idea of stochastic equicontinuity is just relaxing this. So I'll let this probability be something small. So what we're doing here is just letting this probability be less than eta. For every eta, I can figure out all these epsilon and delta such that this is less than eta. Lean soup means just this is stating it for a sequence of functions. You can state it for a class of functions by saying that soup over the class. Lean soup means basically supremum over the tail of the sequence. After some n, we have this for all f in the sequence. So it looks a little bit technical, but the basic idea you should sort of understand. The basic idea is that the continuity doesn't depend on what function I'm taking. Is this sort of clear? It's like a complicated definition, but it's really not, if you go through this, it's really not that difficult. Okay, so why do we care about this? Yeah, so this is like a one sentence summary. Equicontinuity is a form of uniform continuity along the f-axis. So uniform along the function sort of axis. So what this gives us is this very nice result that if we have a sequence of functions that are like these are random functions that are stochastic equicontinuous at let's say theta naught, then if you pick any random sequence theta hat n, which could potentially depend on fn, and if theta hat n is converging to probably to theta naught, then if I evaluate the fn at theta hat n minus fn evaluated at theta naught, this converges in probability to 0. Why this is significant? Because as I mentioned, if you go back to the proof of consistency, terms like this are really difficult to handle or to deal with. Because let's say this could potentially depend on this. Let's say this, I'm trying to maximize f. This is the maximizer of f. So this could depend on the function itself. So I'm evaluating a random function at a point that depends on the function. So all like the distribution is complicated and everything else. But if I know this fact about the class of functions, then I can say, okay, asymptotically I can replace this with, and then this is converging to the limit. I can replace it with this. Now I'm dealing with a sequence of functions at a fixed point. So these are just random variables. Now I can hopefully sort of analyze this better. Okay, it's a significant result, but it just follows. I'm going to try to assign this as a homework problem. It's easy to try to just use the definition and the definition of conversion probability to prove this. It's just exactly set up such that a result like this holds. Okay, so that's what we're going to use. If you can replace this with something else such that this holds, then we can do that as well. So this is all we need. So we need a property of the sequence of the functions such that when I evaluate the sequence at a random point that's converging to a limit, then I can replace it with that limit. Okay, so far so good. Okay. So back to the M-estimators. So you're analyzing something like this. Theta hat n is argmax of some random function over the parameter space. This random function is constructed as an average of these basic m thetas evaluated at xi. And the idea is that xi's are IID from p theta naught. So I forgot to put an IID here. That's the basic setup. So if you recall, we know that this converges pointwise to a limit, which is going to be, so weak law of large numbers tells us this converges pointwise to the limit, which is m theta, let's say, of x1, one of them, assuming that the mean exists. And this this function appeared in the consistency analysis. So if this convergence is uniform and this limit function, this was m theta, has a unique maximizer, basically you have consistency. For now, we're going to assume consistency. I'm not going to impose conditions for consistency. What we want to understand is how fast you're converging, the type of result that I talked about. So for that, we care about the derivatives of this, not m itself, but the derivatives. So I'm going to use this notation, m theta naught dot. The dot on top means partial derivative. I take the partial derivatives of this function with respect to theta and evaluate theta naught. So let's say theta is in RD. This is the gradient, basically. So it's in R. This is a vector in RD, and then I take the double dot to mean the second derivative, which is going to be the Hessian. So it's a matrix evaluated at theta naught. Okay, so it's similar to the notation that we used when we talked about information inequality and the derivative and the second derivative of the score function. Similarly, I'm going to use, again, double dot m and double dot theta means the second partial derivative of mn, which this is, let's say, with respect to theta. It's also a function of x's, but all these are with respect to theta. Okay. So here's the result. So I'm going to use a shorthand notation. So instead of writing expectation of m dot theta naught, let's say x1, could be xi, any xi, they have the same distribution. I'm going to just write expectation of m dot theta naught. This is a random variable, right? And that they're identically distributed for all of the i's. And I'm taking the expectation of that random variable or one of these random variables. The same goes for expectation of similar quantity. So here's a typical result. So suppose theta is an interior point of omega, which is a subset of RD, and then assume that the expectation of this random variable is 0. Implicit in this is that the expectation exists. And also the second moment matrix exists. So m theta naught, this is a d by 1 vector. So m theta, this is a vector in RD. So m theta naught transpose is 1 by d. So this is a d by d matrix. And expectation, you're assuming that exists. So the second moment matrix exists. And because the mean is 0, this is in fact the covariance matrix of this vector. So this theta naught is the covariance matrix. And this is sort of mild. Furthermore, I mean, implicit in these assumptions is that the derivatives exist. Okay, and then the second derivative exists and is integrable at theta naught. And if I look at the expectation of the second derivative, I'm going to call this v theta naught. I'm going to assume that this is a strictly negative definite. Okay. So what would happen is that because you're maximizing things usually. So you know, yeah. So you know that if you have like a function that you're trying to maximize, if things are smooth, at the maximum, the derivative vanishes and the second derivative is negative, right? This is like negative x squared. And you can think of this guy as basically the second derivative of, so these are all expectations under theta naught, so under the truth. So if you want, there's a theta naught everywhere here. So you can think of this as if I can move the expectation, so this is m theta. If I can move, so if I'm taking the second derivative of this over theta, if I can move it inside, like under regularity condition, this is basically what we have as v theta naught. So this is saying roughly speaking, this is saying that the second derivative of m at theta naught is strictly negative definite. Because you're trying to maximize, let's say theta naught is a maximizer of this, m, you'd expect this to be like non-positive, like less than or equal to 0. You're just assuming that it's not 0. But because it's a matrix, these have the matrix versions of themselves. So this is saying there's no direction that this matrix sort of increases. In all directions, basically, you move along the eigenvectors, you go down, sort of, on the function, basically. But what I'm saying is that roughly the assumption here is that the m dot, like, you're basically assuming that this is invertible. Once it's invertible and you're doing the maximum, basically, this has to be like this. But in any case, this is the assumption that we're going to make. It's very reasonable, you'll see. It's roughly equivalent to just assuming that this is a non-singular matrix. What else do I need? Okay, so I need theta hat n to be consistent for theta naught, and then the sequence mn, that's the main function. The second derivative, this is the Hessian. This sequence B is stochastically equicontinuous at theta naught. That's the technical condition that we will need. So conditions are not bad, and sort of the only, this is doing the heavy lifting of putting theta hat n close to theta naught. Let's say we know this from elsewhere, and this is the only really technical condition that I'm putting here. And then these conclusions follow. So if I define this quantity, the first derivative of theta, I form this. This is like an average times, so you can think of this as basically root n times the average of the derivative. I have an expansion for, so root n, so theta hat n converges to theta naught. If I rescale by root n, you'd expect that this converges to something nice in distribution. We have this asymptotic expansion. So you can write this as this quantity, so the inverse of this times that sequence, plus OP of 1. What this is saying is that this side minus this side is going to 0 in probability. And this quantity converges in distribution to a normal random variable with this mean and this covariance matrix. And combining these two, I can just conclude that this guy converges in distribution to a normal with mean 0 and this nice covariance matrix, which you can see depends on those quantities. So is this roughly clear? It's really an abstract result, but we'll see like an example. So you can apply this to, for example, the MLE, with m theta being the log likelihood. And so this derivative is just really the score function, if you remember. The derivative of the log likelihood is the score function. Under those regularity conditions, these two matrices are actually related. So this is like L dot theta naught transpose, which is the Fisher information matrix. This would be the second derivative of L at theta naught, the expectation would be negative of the Fisher information. So this is the Fisher information, this is the negative of the Fisher information. So for that particular case, these are basically sign flips of each other. And so this guy would simplify. So if I have, let me go to the conclusion here. So if I have the MLE, let's say univariate for simplicity. Actually, we don't need univariate yet. So multivariate. This is L theta of x, which is the log p theta of x. The first derivative is the score function. Under those regularity assumptions, we know that's zero mean. So if you assume that you can interchange the integral and the derivative, go back to the Rao-Blackwell under the same, sorry, the information equality theorem. The conditions there, if those hold, then you can exchange the integral and the differentiation, and it follows that zero mean. So we have the zero mean assumption on this, and then this S theta is just the Fisher information. P theta is the negative of the Fisher information. So what the result is saying is that the M-estimator corresponding to this, which would be the MLE, has this root inconsistency result, where this side, that's the V theta inverse S theta V theta inverse. That was the result. So let's say theta is theta naught here, or theta naught is theta. So you plug it in, you can see you get Fisher information and the same sort of the inverse of it on both sides. So one of them cancels out, and the signs would cancel out, and you get just the Fisher information inverse. So what this is saying is something like that. In the univariate case, this is just saying the MLE has this asymptotic variance. So this is 1 over theta is the asymptotic variance, and this Fisher information is the Fisher information of the model for a single sample, if you recall. So you have an IID sample of like p theta, and this is the Fisher information of p theta, the information in one of the samples. And so 1 over the Fisher information is the asymptotic variance. So an estimator that satisfies a result like this is called asymptotically efficient. Why it's called asymptotically efficient? Because we know from the Rao-Blackwell theorem, sorry, the Kramer-Rao bound, that if delta is unbiased, let's say, for theta naught, then under the regularity assumptions, the variance of delta at theta naught is going to be lower bounded by 1 over I theta naught. This is the Kramer-Rao bound, right? So this is like a non-asymptotic result. So for any unbiased estimator for theta naught, the variance is at least 1 over I theta, can be less than this. And those that achieve this are efficient in the sense that they have the smallest possible variance. So those would be UMVUs. So this is like an asymptotic version of that. And for the longest time, people thought that this prevents this asymptotic variance to be anything less than 1 over I theta, but it turns out that that's not true. So you can think of this as a statement of saying that this is asymptotically unbiased for this, because it's converging to that. Or you can think of this as like this is the asymptotic, basically, bias here. And the asymptotic bias is 0. It doesn't mean that the expectation of this is converging to this, unfortunately. And it also doesn't mean that the variance of this is converging to that. If it was true that the variance of this is converging to that, I could take the limit, so I can apply this to theta hat MLE. This would be a function of n, basically. To be precise, this would be like a function of n. So it can apply it to theta hat n, and then let n go to infinity, and it would follow but if this statement holds, even we don't know that the variance is converging, let alone converge to this. But what we say is things are asymptotically efficient if exactly something like this holds. Okay, this is good enough for us. And then there are results about how much you can violate this. So can there be any estimator that sort of uniformly has a smaller asymptotic variance than this? And under some regularity assumptions, you can't violate this except at a set of like measure 0 under the Lebesgue measure, something like that. So this was like a lot of so there's a lot of development in classical statistics related to these ideas. If you're interested, there is some nice discussion of it in Lehman's book towards the end, and a lot of it in the asymptotic statistics book by Lacombe. I might talk about that in the next slide. But this is the idea. Most people just are happy with this statement. So if you have just the result for the MLE, then you have MLE is very general. So this translates to a lot of results in many examples. But the result that I mentioned is even more general. It tells you what would happen for a general M-estimator under some regularity condition. So is this clear? Example. Efficiency, sort of asymptotic efficiency, things like that. This is telling you that the MLE is sort of good asymptotically. So asymptotically, if you believe that you can't violate this at too many thetas, then no matter what your parameter is, you're asymptotically estimating with the smallest possible variance. So you need asymptotically the minimal amount of samples for a given accuracy. Okay. Questions? No questions. Okay, let me try to prove this, sort of. So a couple of things to note first, that the only thing that I really need to show is this expansion. Once I have this expansion, this is easy. Why this is easy? If you look at the definition of this and assumption A. This is the CLT basically. Yeah. So this is saying basically root n delta n theta naught sorry, delta n theta naught is basically root n 1 over n summation I from 1 to n m theta naught dot xi minus 0. Okay, and by assumption, this is just the expectation of m dot theta naught. So what I'm saying is that the sample mean. So once I fix theta naught, this is a random variable, and this is its expectation. And these are IIDs, so this is the sample mean of a bunch of IID random variables. And this is the population mean. So this is exactly the statement of the CLT. So root n times the sample mean minus the population. This converges in this distribution to normal 0 and the covariance matrix of m dot theta, which is exactly this. Okay, this is the multivariate CLT basically. So multivariate CLT. So now if I have this and this is also quite easy to conclude. If you recall, we had a result that said that if a sequence converges in this distribution to something, and I have another sequence whose difference with the original one is OP of 1. Let's go back up. So this result, if a sequence converges in this distribution to something and another sequence yn I have another sequence whose distance to the original one is going to 0 in probability, then yn is converging to x. So this is like saying xn converges in distribution to x, and yn is xn plus op of 1. Okay, that's our notation. Then yn is going to converge in distribution to the same thing. Okay, so if I have another sequence, which is the original sequence plus op of 1, then I would have the same asymptotic limits for yn. This is exactly the situation here. This is my yn. So yn is equal to xn plus op of 1. If I can show that this is converging to the desired limit, then this has to converge to the desired limit. And I can figure out what the limit of this is in distribution. How can I figure out the limit of this guy? I know this. Can I say something about the limit of this in distribution? So you have, let's say delta n theta naught converges to z, some random variable. Then I want to conclude that negative v theta naught inverse, that's a matrix times delta n theta naught, this converges in distribution to something. That's the Stochastic theorem. So this is just going to converge. This is like, it's actually, there are two things. Like you could do Stochastic, or you can just say continuous mapping theorem, because it's just a, let's say this function, negative v theta naught inverse. This is deterministic times x. This is a linear function. And linear functions are continuous. So this is going to converge to, this is like f of theta and theta naught. This is going to converge to f of z, which is negative v theta naught inverse times z. But z is a normal random variable if you multiply it by a matrix. Because 0 mean, the mean would be 0. And this is what would happen to the covariance. So if you multiply a random Gaussian, suppose I have a like if x is normal, which means 0 and covariance sigma, then ax would be like normal 0 a sigma a transpose. That's what would happen to the if A is a matrix. This is what would happen to the covariance matrix. It's just a simple calculation you can do for yourself. So this expression is nothing but the covariance of this after we multiply by this guy. So the result follows if I just show this expansion, this asymptotic expansion. And this is the same idea that appears a lot. Classical statistics, you try to expand this, as we'll see, using the Taylor expansion, and then you simplify things. These are the terms that you like shove under the rug, and this is the main term, and the main term you sort of can deal with by CLT. So we need that asymptotic expansion, and then you're done. Okay. So how do we do this? I'm going to talk a little bit about this because this is interesting. The idea is to start from the first order optimality condition, because I'm assuming that theta at n is converging probability to theta naught, and theta naught is in the interior. I'm going to eventually be close to it, so I'm going to be in the interior, let's say. So when I'm trying to maximize a function over an open set, the function is differentiable at the optimal value. The derivative has to be 0. Okay, that's the first order condition. That's the first thing people do when they try to find the maximum. Take the derivatives that are equal to 0. That's the stationarity condition. In the interior of a domain, basically, if you're maximizing and the maximizer is like within a ball included in the set, then because in every direction I have to not be able to improve, then you write that it means that the derivative has to vanish. Okay, this is clear, right? That's what we need. In fact, this is the only thing that we need. So this proof works for any stationary point, basically, not necessarily the maximizer. So any roots of the this equation, in the context of the MLE, any root of the score equations, basically, would have this expansion. So now we do the Taylor expansion. So this is implicitly you're assuming that this is differentiable. The second derivative exists. So if you recall, a simple Taylor expansion is something like if I have a function, let's say I'm evaluating at theta hat n minus theta naught. This would be the first derivative evaluated at something in between, and then times theta hat n minus theta naught. This is sometimes called the Lagrange form of the remainder in the Taylor expansion. So theta tilde n would be something between theta hat n and theta naught. So I'm applying that in like that to the first derivative. So this would turn out to be the second derivative. So I'm expanding the first derivative. So the first derivative of the first derivative would be the second derivative. So that's the equation I get. The fact that I can write it as at the middle point, I believe it requires some sort of a continuity assumption. Just verify. This is not necessarily. It's like the check Lagrange form of the remainder in Taylor expansion or Taylor's theorem. I believe this is enough that this guy exists, or it may have to be continuous. If it needs to be, let's assume that. But the fact that it exists should be enough, I believe. So we have this expansion, okay, and we know that this side is 0. So this is 0, right? Because theta hat n is converging to theta naught, and I know that theta tilde is in the line segment between them. Theta tilde has to also converge to theta naught. It's really like intuitively clear. You can formally prove it. So theta tilde n would be theta naught plus OP of 1. That's where the notation comes in handy. Right. Now I'm gonna so I have this random function evaluated at this point, which is random, potentially dependent on everything else. I want to say that the difference of this and the limit, because this is converging to theta naught, I'm replacing it with the limit. I want to say these are closed. So this is this plus OP01. This follows from that result that we said about the stochastic equicontinuity. That's the part that I really need to sort of worry about this, but I can avoid worrying about this if I have that stochastic continuity of this sequence of functions, which I assume. So I can replace this argument with the limit and pay a price of OP01. Okay. So we dealt with this expression. This one is simple because this is an average by the V-claw of large numbers. Everything works for the CLT, the V-claw of large numbers. So what we can do now is, what do we need to do? Oh, okay, so I need to also deal with this now. So this is also an average. So if you look at, this is this guy, the first derivative, I put a dot here, it's just putting a dot there. If I take the second derivative, I'm gonna put another dot there. So the second derivative of Mn is just an average. The first derivative is also so. So because it's an average, by the V-claw of large number, it converges to the mean. So this is going to be the limit, which is this guy, plus OP of 1. That's the V-claw of large numbers. But this quantity, if you go back, what we had this notation. We called this V theta naught, so it's just V theta naught plus OP of 1. So I'm saying that this guy is this other guy plus OP of 1, and this other guy itself is something else plus OP of 1. I can plug it in, and I get OP of 1 plus OP of 1, which is going to be OP of 1. So I get OP of 1. Remember, OP of 1 plus OP of 1 is OP of 1. That's the Slutsky's theorem. So just plug this into this guy, you get V theta naught plus OP of 1 plus OP of 1, and then just the OP notation is very helpful. You can just simplify. So we're done, actually. So we dealt with this term. This term is now something I know, plus OP of 1. Now what I want to do is like invert, because I want this thing, but this is bothering us. So we multiply by the inverse. So if I look at the inverse of this by the continuous mapping theorem, because this is, I'm just plugging this guy in. And then I can move the inverse inside, say this is little OP of 1. So if you think of the continuous mapping theorem, this is justified by the continuous mapping theorem. This is a sequence that's converging to this. I'm taking the inverse, and I can basically apply the inverse to the limit. And so this minus this is converging to 0, or this is converging to this in probability. So if you think about this, this step is really just the continuous mapping theorem applied to the inverse function, or the Slutsky's theorem if you want. Okay, so not only this holds, and the fact that I can do this is because this is invertible, right? So we need sort of continuity at the limit, but we assume that this is invertible, so this is all justified. So okay, so now I can write theta hat n minus theta naught. I just multiply by the inverse. That's just the Taylor expansion. This is just nothing but multiplying by the inverse of this. I figured this guy out, so I can just plug in d theta naught inverse times OP of 1. This one was 0. Sorry, this one was 0 by. So this is 0 by the first order optimality. And so I get to now multiply out. So if I multiply out, so basically, okay. So I'm multiplying things out and also multiplying by root n. So this is going to be d theta naught inverse negative d theta naught inverse mn dot theta naught plus OP of 1 or minus OP of 1 times mn dot theta naught. And then I'm also going to multiply everything by root n. Multiply everything by root n, I get, and I move root n inside this. So I get root n. This is just the first term multiplied by root n, and then move root n inside this as well. So if you just compare this statement and this statement, the difference is just that I'm multiplying by root n. Okay, so I now have this nice expansion. If you think about this, this is just that thing that I define as delta. Just go back, and this is just delta n theta naught. I have the average multiplied by root n. So the only thing that I need to worry about is to show that this is little OP of 1. Okay. So this is going to follow if I know that what is in brackets is big OP of 1. If it's bounded in probability, then this is going to 0. This is little OP of 1 times the big OP of 1. It would be little OP of 1. But this is going to be big OP of 1, right? Anyway. Yeah, great. So by CLT, this is converging distribution. And anything that converges in distribution is going to be bounded in probability. So we know that this is true, then this is going to be big OP of 1. Little OP of 1 times big OP of 1 will be OP of 1. So this OP of 1 and we're done. Okay. So proof is really not that difficult. It's just you can see the OP helps a lot. So if you want to write things using sequences, you have to define multiple sequences. But once you're comfortable with these O notations, you can do these calculations. We have to worry, for example, about this. It's not necessary that something that's OP of 1, this could blow up. But because it's converging in distribution, it's going to 0. The key step is just this, how we dealt with this guy, which is the only technical condition that we need. And the basic idea is just write the Taylor expansion. And because of the Taylor expansion, I can relate the deviations of this function to the deviations in theta. and then just inverse, take like the reverse or invert the transform basically. And by CLT, I know what happens to these guys, and I get an expression for that. And okay. So now we have this very nice result, and you can see you can control the asymptotic variance by constructing this M theta. This is sort of, these two conditions are sort of saying that things are like M is correctly specified. So if this is true, like this is equivalent sort of to the population version of the function having a maximum at theta naught. And this you can think about what it says. It just, for log likelihood, for example, it just automatically satisfied. But once you set this, once you satisfy these basic conditions, then you have this nice asymptotic result. You can try to engineer M so that you manipulate the asymptotic variance if you want. Okay. Questions? So I suggest you go through this. The proof is very simple. Once you get comfortable with these ideas, we use a couple of these tricks, let's say, or properties, but nothing very fancy except the stochastic equicontinuity. So I think this is correct, but I'm going to hopefully post it as a homework problem. If you want to prove something like that, if you have conditions on the third derivative, you basically can sort of show this. I just assume that this stochastic equicontinuous. If you know, you can go to the third derivative, and the third derivative is like bounded by a function. That function is integrable. It's bounded uniformly in the neighborhood of theta naught, and then that function is integrable. You can, I believe you can show this. I'm going to try to post it as a homework problem. Usually these things are stated for the log, the MLE, so this would be like the third derivative of the log likelihood. So if you can control the third derivative, then you're fine. But like again, classical statistics people have tried to reduce these conditions. What if I don't have third derivatives? Can I get away with less than third derivatives and even less than two derivatives? Sometimes you can even without having the second derivative even. But let's not go there. So just to illustrate the ideas of how to do this. Once you know how to do it, then you can try to figure out more complicated, more relaxed, more general statements. Questions? Okay, let me maybe say a few words. Online people, are you okay? A few words about this super efficiency. That's the idea that if you have an estimator, let's say delta n, for which you have this asymptotic statement, as I mentioned, if you have an asymptotic statement like that, you'd say that delta n is asymptotically unbiased for theta with asymptotic variance sigma squared theta. Like the common assumption for a long time was that the sigma squared theta has to be bigger than or equal to 1 over I theta, which is the Kramer-Rao bound. So asymptotic variance has to also be lower bounded by the Kramer-Rao bound, or what Kramer-Rao bound suggests. And Hodge's example, or this guy, like a classical statistician, came up with an example which sort of completely shattered that idea. And the idea is that I can actually be, if you pick any point, I can be arbitrarily better than this at any given point. And then everywhere else be as good as this, but at a given point, I can be much, much better. And the idea was to consider these shrinkage estimators. So if I have delta n satisfying that, then I would, I constructed another estimator that's equal to delta n everywhere, except when this is very small. So when this is small, let's say less than n to the negative 1/4, I'm going to scale it down by a factor a, which is, let's say, less than 1. It's not hard to argue that this guy has to have the same asymptotic behavior for anything that's, for any theta that's not 0. Anyone knows why would that be? Yes, so it's related to, so this delta n is going to be like within a radius of 1 over root n, as I mentioned, of theta. And let's say theta is 0, right? It's asymptotically root n consistent. So it's going to be like with high probability within an interval of, let's say, length 1 over root n on both sides of 0. How about 1 over n to the 1/4? Is it smaller or bigger? This interval is bigger than the other one, or let's say n is 10 to the 4th. This interval would be like this, right? And yeah, this interval would be 1 over 10. So you're right. So if you're not close to 0, like we're theta naught here, this guy is going to get close to theta naught, which is non-zero. And so it's not going to be in this interval. This is like an interval around 0. So if theta naught is not 0, delta n is going to approach this and eventually would fall outside. So this is, okay, how can we? Let me try to do it better. So this is this interval, and then I have a much bigger interval, which is like 10 times bigger. This is 1 over n to the 1/4, negative 1 over n to the 1/4. Imagine like n being that, so this would be like negative 1/10. So if theta naught is positive, so these intervals are shrinking. So if theta naught is positive, eventually delta n is going to be close to this guy, so it's going to fall outside this interval. And so this is not going to matter. So this is not in effect. This is in effect, so it behaves like delta n. So for any theta naught that's not 0, this behaves exactly like this asymptotically. For theta naught, which is 0, eventually I'm going to be in an interval like this with high probability, and this is certainly inside this. So eventually everything happens in this region. So this is going to be, basically delta n is going to be the same as this asymptotically at around 0. And because of that, if you have an estimator that's just a times delta n, by continuous mapping theorem, you can argue that, so that like, you know that root n delta n converges in this distribution to normal 0, sigma squared theta naught is 0. So root n a delta n is converging to normal, it means 0. By continuous mapping theorem, you have to multiply the limit by a, so it's going to be a squared sigma squared theta. Right, so and delta n basically is the same as this. If you sort of try to make this argument a little bit more precise, the ratios of these intervals are also going to 0. So like this interval eventually contains all the mass, and so the asymptotic I can so engineer an estimator whose asymptotic variance is the same as the original one except at 0, at which point I can get this. I can make a as small as I want. Even I can make it 0. If I set it a equal to 0, I can make it 0, have 0 variance at theta naught. So I can be super efficient. Super efficient means super better than the efficient estimator, which has this variance. Imagine MLE that has this variance. I can beat the MLE at 0 and everywhere else be as good as the MLE. It's like a form of admissibility, asymptotic admissibility. So the thing is that this sort of resolve the issue whether that's necessary, it's not necessary. But then like Lecombe and other people prove that this can happen only this can happen like in like a proper interval or some big set. The set that this can happen, that you can beat this under some regularity assumptions, is of Lebesgue measure 0. So things are still quite good. Okay, this is Hodge's superefficient example. There are other examples that you can build. Any other question or any question? Okay, so now you know about efficient estimators. You know to be careful about like asymptotic efficiency. The MLE is generally asymptotically efficient. Okay, before getting into some of the applications of these results, there's another tool from asymptotic statistics, which is very useful for us. And this is called the delta method. Anyone has heard about the delta method? Okay, so it's just really another application of the Taylor expansion. So this is saying if I have basically an asymptotic result like this, an, let's say this could be root n, a sequence that's going to infinity times xn minus theta converging in search to z, I can get a limit theorem like this for some f applied to xn. So I can get asymptotic normality results for nonlinear functions of my random variable easily. And the thing that appears here is the Jacobian of the transform. So if f is, let's say, from Rd to Rk, you notice there's this Jacobian, which is like the derivative of a multivariate function, or characterizes the derivative, total derivative. So it's a matrix whose jth element is just the partial derivative of the fi, which is the ith component of f, with respect to the jth argument. Okay, so hopefully people are familiar with the Jacobian. So there's a matrix, and then this Jacobian evaluated the true parameter theta here is actually, this doesn't have to be true parameter. Whatever parameter appears here appears there, and also in the Jacobian. So evaluate the Jacobian at that point. I'll leave the proof to you guys. It's just I'm gonna skip. The proof is very similar to the ideas of U. So you just write down the Taylor expansion and then try to argue. Okay. The idea is that once you get, this is sort of forcing you, because this sequence is going to infinity. This is big OP of 1. So this statement tells you that an xn minus theta is big OP of 1, which is saying that xn minus theta is big OP of 1 over an, and an is going to infinity. So this is little OP of 1. And so xn is close to theta, so I can expand. So I just expand, so xn would be f theta plus the derivative, which is just going to be the Jacobian, sort of Jacobian of function at like value of theta times xn minus theta plus the remainder. So you have to worry a little bit about the remainder, but there's nothing that serious about this. And so I get multiplied by root n. I get root n here, or actually an, let's say. I get an here. This is converging to z by continuous mapping theorem. This is going to converge to j theta z, and then the rest you have to worry that this is like OP. So an times this is OP of 1, which is going to be the case. You can argue easily that that's OP of 1. So it's just an application of the Taylor expansion. I'll let you figure out the details. Okay, it's a good exercise. So in the univariate case, let's say f is from R to R, then this is just the derivative. Okay, so let's see an example of this. So if I have xi's are IAD, with mean, mu, and variance sigma squared, I have the CLT, which is this statement here. Now, suppose I apply delta method with ft being t squared. So I get that f of x bar n minus f of mu root n here. This is going to converge to f prime of mu times the normal. So f prime of mu is 2 times mu. So effectively multiplying the variance by 2 mu squared. So this gives you another normality result. This works everywhere except that mu equals 0 once I have mu equals 0. This is true, but this is telling you that you're converging to a normal with mean 0 and variance 0, which is just 0. So what do we conclude if we get something like this, converging to 0 in distribution? Sorry? Yeah, converges to 0 in probability as well. What it tells you is that this is not the right order of convergence. There's still more, so I can multiply by something bigger. Because multiplying by this, still I'm going to 0, so I have to go higher. So what happens is, this is true in distribution and in probability, right? But then you can go do the Taylor expansion. What happens in Taylor expansion is that the Jacobian or the derivative, the first term would be 0. And so you expand it for another term. So you get the second derivative. And if you remember Taylor expansion, there's a quadratic form. So instead of converging to f prime mu times z, you converge to like z squared. So you can easily show that in this case, if you instead of root n multiply by n, this thing would converge to a chi-squared, scale chi-squared. And so the delta method in general does that. So if you end up sort of having a vanishing first term, then your results sort of upgrade to the second order Taylor expansion. And instead of, for example, for the normal case of getting a normal limit, you get a chi-squared limit. So again, I'll let you figure this out. This follows easily from CLT as well, because we know that this is converging to a normal like this, so the square would have to converge to chi-squared. But it follows from the delta method. Yeah, something like that. So if you have a statement like this, and f is differentiable and the derivative vanishes, then instead of root n, you put n here, and then things would converge to a scale chi-square. So once you understand how the delta method sort of is derived, then you can also derive something like this. The similar idea, I'll let you go through it. You can just play with this. It's a very fun result to play with. You can sort of play with it in the Bernoulli case. You get an interesting result. It works. Like, for example, if you have the Bernoulli, you can try to estimate the variance by the plug-in estimator. So this is the sample mean and estimator of P. This is the variance. So I can plug in the variance. This f of x bar would be an estimator of the variance, and I would have an asymptotically or asymptotic normality result like this. Again, if P is, that's the derivative of this basically. If P is equal to 1/2, then things vanish. So you'd have faster convergence basically at 1/2. Things are better. So your estimator is better basically. So you'd upgrade it to n times that, and you get a result like this. Okay, questions? Okay, we're almost like done. There's this multivariate version, which I mean, this is another example of things. I stated things for the multivariate case. You can go through this yourself. Next time, we're going to talk about the use of these asymptotic normality results. As I mentioned, mostly they're used for two things, asymptotically comparing estimators. So you can compare the asymptotic variances because you reduce everything to these asymptotic variances. And then this tells you something about the performance. And then the other one is building these confidence intervals and doing these hypothesis tests. So next time I'm going to come and talk hopefully about these things, and then we're done with asymptotics. Okay, questions, comments? Okay, thank you guys. Thank you online people. See you on next Tuesday.